Continuing on with class 23, we're going to do some more comparisons between the MATLAB and SolidWorks dynamics force analysis. Here is the, I think this is Norton's problem 11, example, 11.2. And so let's take a look at the differences between doing a full rotation and doing a partial rotation. We won't do this for the others, or at least not much. Let's see, I did this right here. Okay. Trying to figure out how to get these both to display at the same time. It's being a jerk. I think I need to turn my computer off, turn it back on. And come in and that one right there. Okay. So here is the crank slider conversion right here. So we're converting a crank slider into a full rotation. So a lot of the stuff right here, we stay the same on the left-hand side. This is the single point. I don't think much changes. I think perhaps I should have gotten rid of a theta. No, I did get rid of it. Right? That's actually in the 4 bar. I accidentally left that one in. So if you look at the code, there's a theta 2 that doesn't matter. But we have removed the theta 2. So technically speaking, this is one of the ones that changes right there. I guess we do change that. We remove it down to the bottom. So we start getting into this section down here. And, this position analysis for this. And we don't have to do much of a position analysis because it's just a triangle. And all we need to find is theta 3 out of it. All right, so all we need is theta 3. We're given theta 2, and because they're in line with each other, it's not that difficult of a position analysis. So we do a position analysis. Then with that, we need to have the position vectors for everywhere. But now if theta 2 is changing, we're going to have a string of theta 2s. And also, we're going to end up needing a string of omega 2s as well. And and I think we will create a string of alpha 2s. Is that right? I think so. Well, let's just keep doing this for the time being. So I established this is my alpha 2. No, we don't need alpha 2s. I'm sorry. It's a constant angular acceleration, so that's why. And it's decelerating, actually. We do create a string of time, and I decided to go for 4 seconds long. I think that I did that, and I do mention this, I think, in class 21, where I describe how I went about trying to get the mechanism into the angle position and the angular velocity that I wanted to by finding a good, or working backwards in kinematics and finding what angle I would need to start at in order so that when it reached the angle of interest, it was traveling at the angular velocity that they specified, which is like 20 radians per second. It's actually over here, right? They say, 30. 30 and the angle, the theta 2 in there, was at 60 degrees, right? So in order to get that, I have to go over here and have an initial angle of 2.3335. I just turned it into radians. And then I used this initial velocity of 40, and then it decelerates because of that negative 10, and I'm able to get the thing I want to do. I populate all the outputs with zeros, so that the correct string length, and then here is where I get my angular velocities, I get my angle theta 2s and omega 2s. I decided not to call them, whatever reason. I keep changing the names of these things. It looks like I went back and forth between there. That's sort of weird because it was the opposite of what I did in the previous example, but What can I tell you? I can't say I'm consistent between things. So we got those strings going for us. That's nice. Now we do a position analysis so we can find out what all the theta 3s are going to be. So we had all the theta 2s. Now we have all the theta 3s. So this was just a particular theta 3. Here we do all of them, and it's just a string command. So that's nice. From those positions that we got up above, we can find all of the position vectors at every time step. And so that's what we do for both links 2 and 3. And now we do a velocity analysis. That's a pretty easy one. This is based on equations 622a and 622b to find the omega 3 and also find the velocity of the endpoint or piston if there were a piston. Then we do an acceleration analysis. This is a little bit longer. That is equation 716d. And we also want to find the accelerations at different points. So we have the angular acceleration, but we also want the acceleration at B. Let's see if we can get that up there. At B, and also the acceleration at A. So that's what we do right here. Now with those accelerations in place, we can go ahead and solve that same matrix that we did before, right? So that remains the same. Are we in a for loop? Yes, we're going to for, right? So it's going step by step at each time step, and it's doing that, and it's populating the output. Some things we don't need, and then they get reused. But we end up with a B, and each time we get a B, we harvest out the forces that we want out of the thing, and then also get the torque. And so then we have the plot. So let's take a look at the full rotation here. Here is what it looks like. And do I have any Excels open? I probably want to close this Excel. I could actually start using this with something else. I should change it into an actual save as an example, and then maybe I'll put it all into the same place. I'm going to put it into a new version of Excel. I don't know why it's going into the older ones. It's for some reason. I don't know what that reason is. And I'll go miscellaneous onto this, and I'll just say F24 ME501 class. I think we're in class 23 examples. And then I can put them all in one place. And in fact, if I want to be really lazy, I will put them into here. Boom. And I will just replace them underneath there, right? I'll just go right there, and then this thing will adapt to it because I am extremely lazy. I mean, you wouldn't even know how lazy I am, but that's good. It's good to be a lazy engineer. So let's go back into here, and we will uncomment and hit it again. Boom. I keep getting that. It keeps jumping over to the other screen. So let's see if we got to go back onto where I keep this examples, and there you go. And we can just be lazy. Long string, much longer. We're gonna have to. Wow, that's really long. I guess it was 4 seconds long, so that kind of makes sense. But we're gonna now we're in for it. No, it's not gonna want. Yeah, there you go. All right, so I can't change anything while I have that in the copy and paste thing. All right. So, all right. So what I have to do here in order to get this thing to work is to, well, there's a couple different ways to do this. Here's a cheater way. You see that's 4002, right? So I don't want to drag this thing all over the place, but I can go to that right there and go 4002. There you go. 400. And then go 400. And am I missing anybody? I think so. That's fine. Boom. Bang. And then make this into what? We'll give the default first. Boom. Right. So there goes default. And I don't like go 4 seconds. Boom. What's the point of that? Okay. And now let's try to see. I'm going to close that one down because this one really seemed, when this was open, it seemed to really make the SolidWorks angry. So let's go over to the SolidWorks if we can. All right, it's going to really cheese me off here in a second. Why, oh why are you the way you are? So that's like a little thing my daughter and I say to her. Goes, why are you the way you are? And then she'll reply, why do you hate me? And I say, because of the things you do and say. Does that sound like a healthy relationship? I think it is. All right, so let's see this thing in motion. What an odd looking duck. What an odd piece. Look at that thing. It looks to me like it's a very sleepy or almost a playing dead possum. That's what it looks like to me. I chose those colors too, but I also put that little what I think of as the crash test dummy symbol on there. So anyway, I think I'd previously discussed how I was able to get this thing to match the kinematics. I messed around with the motor into here, and I used data points. And I was able to find the angular velocity or make an angular velocity versus time type of thing, placing it onto the motor. And as I pointed out in the previous video, I took the forces here and I put the motor torque and I did about the Z component, and then I went down here and I picked the motor. And when I did that, boom, it gives me this nice little graph. And if I go to that graph on down to here and go export to spreadsheet, it gives me a friggin' Okay. Well, that's just upsetting. There's nothing open. Can we just save it? How about we save it? Oh, maybe it's because I've selected that. Oh, maybe because it was selected. It didn't want to do it. Let's try it again. Maybe that's it. All right. I'm going to pause it again, and we'll try to figure out why that does that. All right. I have zero idea why this worked. I clicked around a bunch of things and closed some things, and I finally got it to work. Right. So it exported, and now we can just take these and... These are much shorter. So this is like 1/10, because I'm at like 401 right in here compared to what I was over into this one. We'll see. So I'll go there to there. And that doesn't seem right. Oh, I know why. Okay. So, interesting. Why are these so much different from each other? All right, something just really weird just happened. All right, there's the SolidWorks. It's the magnitude has really, really changed. Is one of them in inches and one of them in feet? Because it does look like that could be 12 times the thing. It says it's in inch pounds. Oh, wait a minute. Is my SolidWorks somehow in... It's in inches. It says pound force inch right here, but my Oh, you know what happens sometimes? What you got to do is you have to go back. Sometimes there's a little bit of a issue. I don't understand, but you have to do this twice. Nope. that seemed to make it worse. Go back to edit features. You gotta like just change something, and you still have this crazy amount of discrepancy there. I don't get it. Yeah, we're in the thousands in this one. Get rid of him. Do not keep a large amount of stuff on your clipboard. Yeah, we're in the thousands. Don't know why right now. Doesn't seem to line up. Doesn't match up. What about the this thing right here? And what do we say we went? Did we say 401? Did we say 401? Yeah, not doing a great job of matching on this one. But that's all right. It's all about the perseverance. We want to go to 402. So click on here. No, click on here. All right, it's mad at me now. Just don't crash. I'm not recording this video again, man. I don't know why it's doing this thing on me, but I gotta investigate. All right, so we got it right onto there. You can see that they're pretty well scaled off of each other, not identical. Something's out of whack in terms of the values that we've placed. Could be masses, and I don't know if I've ever done this before. Actually, I actually have to confess, I don't know if I've ever measured these two things versus each other. So this is probably not the best time to do it, but this is typical of being an engineer a lot of times. Like, what would happen if I went like this and divided by 12? Boom. That's an ugly number, but I just go down like that, and then I come over to here, and I just go that. Boom. Interesting. Not matching up perfectly. I may not have started at the exact right spot. That's what I'm starting to think about, but that wouldn't be the reason why there's so much. But this is actually a little bit more like 10, I would guess. I'm guessing. A factor of 10. Yeah, they're way closer to like being like 10, not 12. But that's actually more on the tips down here, but not down over here on the bottoms. And there's like a phase shift taking place. That might be explained by where we're starting out. So this deserves a lot more explanation, but I don't have the time to mess around with it. I want to finish up the videos that I'm making. But I mean, diagnosing why this is wrong is kind of like an important engineering thing to try to get them to matching data, and not just giving up too easily. But at some point, the time runs out. Never fudge anything, but we definitely want to explain every single disaster, every single thing that's different. Right there. Interesting type of problem. I don't know why we can't get it to match, but do your best to get it to match anyway. So that's the end, I think, of this video and this little sleepy possum guy. I wish I could figure out right away. There is a force on here. If you take a look at that force that gets applied to the thing, too bad we can't see it all the time as it's moving around, and make sure that its orientation is a 50-pound force. That is just a strange dude to have on there. But I believe it's also matched in the in here. That's the FP, wherever the heck it went. Right, this guy. That's the 50 pounds that we're applying onto the thing, and its orientation. I'm not sure we used... here's one that I don't know about. I don't know if I was able to get, and I doubt I was able to get a coefficient of friction thing into my part. In fact, I know I didn't. And I mentioned that I think previously that I did not get a... although I was able to... That's interesting. I was able to fairly well match the values when it was stationary. I don't know. I'm just trying to hammer home why that might be different. You don't have to listen to this whole video, I think, but just trying to show you some of the techniques that I used to try to match these up, and they should match up, but I apparently haven't before. We'll talk to you soon again with more matching of MATLAB and SolidWorks for dynamic force analysis.